All right, chemists, today we're going to talk about combustion reactions. Those types of reactions that are near and dear to everybody's heart. It's always the exciting ones when we do some demos and reactions every year. Now, combustion reactions, we're all a little bit more familiar with them than, say, some of the other types of reactions. But the definition of a combustion reaction is it's a redox reaction, right, oxidation reduction, that's characterized when a compound of some sort is oxidized specifically by oxygen gas. So oxygen gas is always going to be a reactant in this type of reaction. And the other big characteristics or big ideas is that this type of reaction is always going to be exothermic, right? Combustion, fire, it's always giving off heat, light, and energy of different sorts. Usually in these types of reactions, the oxygen gas is coming from the air in the atmosphere, but that doesn't have to be the case. It could be provided by some other compounds that have decomposed and released oxygen gas when they do that. But we'll talk more about that when we do decomposition reactions next time. Um, then, in terms of the combustion itself, a lot of times when we burn things or we think of combustions, there's a wide range of speeds at which that can happen. Everything from a candle burning to the explosion of C4, all of those are combustion reactions, but the rates, right, how quickly those happen, how quickly the energy is released, can vary depending on a lot of different things, such as how quickly the oxygen is made available, the size of the compounds, how easy they are to break apart, etc. Now, in terms of predicting the products that are going to form here, unlike synthesis reactions where those reactants just come together to form a product, when we have a combustion reaction, one of two things is going to happen, and it depends on what the reactant is that is not oxygen. Now, if that other thing is just an element, right, a single atom or a diatomic molecule, essentially what happens is that compound synthesizes, it combines with the oxygen to produce an oxide. So here we have a little bit of an overlap between synthesis and combustion, where if it is just an element, they end up joining together, they oxidize to form the oxide compound. However, usually when we think of combustion reactions such as gasoline, candles, campfires, all of those kinds of things, the compound that's being oxidized is often what we call a hydrocarbon, and it's a compound that contains a mixture of carbons and hydrogens in different ratios. And sometimes, depending on the product, there could also be some nitrogen in there sometimes. Now, when a hydrocarbon combusts, the product is always going to be CO2 and H2O because that's the most stable bonds that can be formed between oxygen and hydrogen and carbon and oxygen. So when given this scenario and those atoms recombine, those are always the combinations that they go into. If nitrogen is in the compound, it forms N2, right, nitrogen gas, because that is its most stable compound. Here we have a couple of different examples of combustion reactions. Something that you should notice or take away from each of these is that every single one of them has oxygen as a reactant, right? That's one of our key features. All of the ones that have a hydrocarbon, right, all of these that have some combination of carbon and hydrogen in them, all of those produced carbon dioxide and water as a product. Every single one of this type of reaction is exothermic, right? They're all releasing energy. And all of these are initiated by a little bit of heat. Sometimes that heat comes from a match or a spark or the heat of a wire as electricity is running through it. Right? But anytime we burn something, we do have to initiate it a little bit. Now, in the first couple examples up there, we have iron, magnesium, silver, and hydrogen. All of those are examples of combustion reactions where we don't have a hydrocarbon. Instead, we have a single element. In the first three cases, we have a metal. In example number 4, we have hydrogen gas, right, a nonmetal. All of those look very similar to the synthesis reactions we talked about last time, where that element is being oxidized and joining with the oxygen to form the oxide compound. Let's take a look at a couple of these reactions. We're going to take a look at some videos, and then we'll move on to talking about the mechanisms and the energy changes that happen in them. All right, so first we're going to take a look at the combustion of propane reaction. So here we have propane gas inside the tube. These little vents up here in the nozzle are what allow oxygen to come into this as it's opened up and released. So right now, if I open up the valve, it'll let propane gas out. Maybe hear the hissing, but we obviously don't see anything because the propane gas itself has no color. It's got a little bit of an odor from other chemicals mixed in it to help you tell that it has an odor, but otherwise it doesn't have any either. When we push the button here, it gives a little electric spark, which provides that activation energy to get the reaction going, and it will start combusting and reacting with the oxygen in the air to produce carbon dioxide and water. So we'll open this up, and dial it down a little bit just so you can hear. But in the visible camera, you can't actually see the flame because it's burning so efficiently with the amount of oxygen coming in, the way it's designed. It does not have that same yellow color that like a wood fire does, because as we talked about in the other part of the video, that yellow color comes from the carbon from the parts of the wood that are with the molecules that isn't burning up and going through the reaction completely. But if the reaction does happen efficiently, nothing is visible in the flame itself. But you can still see the reaction occurring from the amount of energy being given off through the infrared camera in the picture. All right, so the next example we're going to do is the combustion of magnesium. So unlike the hydrocarbons, this one's going to kind of overlap with the synthesis to make magnesium oxide. Now, as I said in the video, these reactions with the metals do occur naturally. They just tend to occur slowly. In the magnesium metal, we see that here there's a shiny spot in the center. That's actually where I use a knife to scrape the surface of it. Because if this magnesium is left out normally, it'll actually react with the oxygen in the air to do this reaction on its own, just at a really slow pace. But that's what we see on the left and right here. That dull, darker coating is the magnesium oxide from the reaction that has already occurred. Whereas in the center, right, we can get that shinier bit. Right, that's the actual magnesium metal in the center there. However, even with this little coating on it, if we do provide it with some heat, we can initiate that rapid combustion reaction to get the chain going. So let's take a look at that. The magnesium metal in the infrared camera, it actually has a little bit of a glow to it right now. That's actually from a little bit of the reflection of the infrared light from the sun. And it's also a little bit of the residual warmth just from my hands because it's such a good conductor. It warmed up a little bit as I was holding it and manipulating it. But we'll take our propane torch now and light that. And we'll use that to provide that activation energy to get the reaction going. So there's the combustion of magnesium. Right, we see it's giving off that bright light with all the energy. It's also extremely hot, as you can see in the infrared camera. The reaction died out there a little bit as it reached that magnesium oxide coating again, but we can get it going. That white dust is actually some of the magnesium oxide that gets hot enough that gets sublimated up into its gaseous state to keep going on. The wind here is blowing a little hard. That's actually putting out my reaction as well. Here we have the combustion of the iron metal. So here we have iron steel wool, right? Iron on its nicely fine little strands of it. We'll heat that up to get it going. And then the reaction continues on its own. And again, we can see the light and the heat being given off through the combustion reaction as the iron combines with oxygen in the atmosphere to make iron oxide or rust, right? The really rapid way of making rust. All right, so one of the demo reactions that we saw in the video just now was the combustion of propane gas from the cylinder that we then used for the other combustion reactions to follow. So going through and looking at the energy changes and the mechanisms that happen here, as we've done in the past, first thing we need to do is get the word equation. And we know we took propane gas and it's being combusted, so the other reactant has to be oxygen gas, except this is the word equation, so I should actually write oxygen gas. And since propane is tricarbon octahydride, that's a hydrocarbon compound, we know the products are going to have to be carbon dioxide and water. Both of those are going to be in their gas states. And because it's combustion, it's going to be releasing energy. We use that little bit of energy from the spark to get this reaction going. Turning this into a chemical equation, we have C3H8 for tricarbon octahydride We have oxygen gas, our diatomic molecule, forms carbon dioxide, water vapor, and releases energy. Balancing this out, I see that there's 3 carbons on the left and only 1 on the right, so we're going to address that with a large 3 for coefficient there. There's 8 hydrogens on the left. To make that match, I'm going to put a 4 here. And notice how, I mentioned this back in the balancing equations video, but whenever we have a combustion reaction, it's always simplest if you try to balance the equation by starting with the carbons, then doing the hydrogens second, and then lastly finishing it out with doing the oxygens to make everything match. In this compound, we have a total of 6 oxygens because we have 3 times 2. Here we have 4 oxygens, gives us a total of 10. So we need a 5 for a coefficient in front of the O2. Now the trick is that if when we add these 2 up, it gets to be an odd number, what we can do is double all of the other coefficients to get rid of that odd number. Now that we have our chemical equation, let's take a look at what's going on in the mechanism. Let's take a look at the redox. Let's talk about the oxidation states of the reactants and then the products and what's going on as this thing changes. Now remember from our initial types of reactions video, when something is oxidized, it means that it's losing electrons. In this case, we don't have any ionic compounds. We're talking about that figurative, if this was an ionic compound, what would be happening situation. Really what's happening here is that the bonds are being reconfigured, and some elements are going to be attracting those electrons more than the others, and that's what we're talking about when we talk about the change in oxidation states here. Now in our oxygen compound, those 2 oxygen atoms are pulling on those electrons equally, so neither one of them is more negative than the other, so it would have an oxidation state of 0. However, in C3H8, carbon has a much greater attraction. It has a higher electronegativity, if we remember back to that periodic trend. So here the electrons, the carbon is going to be pulling the electrons further away from the hydrogens. Now each hydrogen is going to be losing an electron, so +1. So in total, because there are 8 of them, we have this 8 positive. Now because this compound overall is neutral, that means that that 8 positive charge must be getting canceled out by the 3 carbon atoms. So to do that, each of those carbon atoms, it's not going to be a whole number, but would need a -8/3 charge to balance it out. If we look at the products, oxygen, each of those is going to pull on the carbon atoms. It's more electronegative with an oxidation state of -2. And since we have 2 of those for a total of -4, the carbon atom here must be +4. Similarly in the water, oxygen is still -2, which means each of those hydrogens must be +1 to give us a total of +2 to balance that out. So in terms of oxidation and reduction, what is being oxidized? What is losing electrons and what's being reduced? What's gaining them? Well, our oxygen atom is going from a 0 to a -2. So the only way that can happen is if the oxygen is gaining electrons. And our carbon atom is going from negative to positive. So it must be losing electrons. Right? It must be getting oxidized. So our carbon atom in this case is starting at -3 for each of those. We can write that as having 3 carbon atoms, each of those having a charge of -8/3. So in total on this left side now, there's a -8 charge. Right? 3 things with -8/3 each is -8. At the end of this reaction, we have 3 carbon atoms, each of those having an oxidation state of +4 for a total of +12 as a product. In order to get from -8 to +12, those carbon atoms would have need to have released or lost 20 electrons over the course of the reaction. And remember, we're not totally losing them, we're not forming an ion, but rather it's donating these 20 electrons to the oxidizing agent. In this case, it's the oxygen molecule. If we look at the reduction reaction rate, what's happening to those oxygen atoms as they get reduced, meaning they gain the electrons, We're going from 5 oxygens, all with an oxidation state of 0. And at the end of this, we have a total of 10 oxygen atoms, each of those having a -2 charge, for a total of -20, which means to get there, we would have needed to gain 20 electrons over the course of that reaction. Now, this is good. This shows that the reaction checks out because we are releasing 20 from the carbon. We're gaining 20 in the oxygen. Right, so that's the changes in the reduction and oxidation states over the course of the reaction.